So this is our lesson 2, plate tectonics notes. Now this lesson, this is the biggest idea in earth science in a very long time. This is the most important concept we're going to learn in terms of earth science, okay? And what we start off with is this idea here. For a long time, people have looked at South America and Africa and said, wow, those two look like they fit together. They look like they match. They have a similar shape. And for many years, people just said, oh, it's just a coincidence. It doesn't mean anything that they look like they fit together. But as people studied South America and Africa, they started seeing weird things. Okay, right here, let's say, right where these two rocks look like they would match up, they find rock layers with the exact same fossils in it. They find the exact same rock layers with the exact same fossils in it. So like, let's say there's a lizard. They'll find little bits of that lizard here in South America, and they'll find little bits of that lizard here in Africa. Even though now there's a gigantic Atlantic Ocean in between, it matches as if those two layers were right next to each other. And that's true here, and it's true here, and it's true there. So what they find here matches what they find here in terms of fossils and stuff like that. And then people started getting confused. People are like, what's going on? This fits this. I don't understand it. Here's some more evidence of this. So people were looking and they found this Glossopteris, which is a jungle plant, a plant that only grows in really tropical environments. They found it here in Australia and they found it here in South America, but they also found it in this long band of Africa. They found it in parts of India, and then they even found it in Antarctica. So everyone's confused. Why in the world would there be a tropical plant growing in Antarctica? It sure looks as if these were all put together like this, just based on where those fossils are found. Okay? This Mesosaurus is only found here, in the tip of Africa and this little part of South America. Okay? Fossil evidence here matches. And it looks like these continents were once together. That brings us to the theory of continental drift. That's the first thing we ever came up with to try to explain what we're seeing, the theory of continental drift. Okay? Now, the theory of continental drift states that the continents are drifting apart. Okay? It appears that South America and Africa were once together because they look like they fit together. And that's kind of simple. But that's the theory of continental drift. Okay, so here's the Earth. Now the second part of this has to do with the oceans. So if you look at, here's Florida, the East Coast, over here's Europe, everything else. Now before, people thought that the bottom of the ocean was just like the bottom of a lake. Just a flat bottom, sandy, like a swimming tub, like a swimming pool or a bathtub, okay? But what wound up happening was, during World War II, there were lots of ships going back and forth across the ocean, and as submarines became more and more important, we decided we need to have a good map of the ocean floor. And so what they decided to do was map the ocean floor using sonar. And sonar is just a sound wave. They send a sound wave down, ping, it hits the ocean floor eventually, and bounces back up to the ship. And based on how long it takes to do that, you can tell, okay, it's this far to the ocean floor. Now, as they did this over and over and over again, they found the ocean floor, surprise, has these big mountains in it. Okay? And here's what it looks like on Google Earth, these big, huge mountains that we see. Okay? This mountain range that they discovered is huge. It extends all the way from up here in Iceland. It starts in Iceland. Iceland is actually a part of the mountain range. It extends all the way down to, it goes past North America, past Africa, around South America, and it goes clear nearly to Antarctica. This is the largest thing, the largest land feature on Earth is this mid-ocean ridge right here. So here's a better picture of the mid-ocean ridge. It's in your notes. and it goes clear up to Iceland here. I think Iceland is the only spot that's sticking out of the water just because for some reason the ridge is higher there. Okay? Well, this wound up leading to the theory of seafloor spreading. Okay? So, during World War II, ship captains took their sonar measurements of the seafloor and realized that there are underwater mountain ranges. That's what we're seeing right here. Okay, this is East Coast, here's Cuba, here's South America, here's Africa. And in between there's this gigantic mountain range. Okay? Here's what we need right now. Samples showed that the youngest rock is near the ridge, here in the middle, and the oldest rock is near the continents. So how strange is that the youngest rock is right here in the middle, and the oldest rock is right here next to Africa, right next to South America, right next to North America. And there's brand new rock right in the middle. So if we take these two ideas and stick them together, we have continents that seem to be moving apart. Let's say this is South America, here's Africa, and we have these plates where the youngest rocks is forming here in the middle, and then it gets older as it pushes apart. You put these two theories together, the continental drift and the seafloor spreading, and you get the theory of plate tectonics. Now, plate tectonics is continental drift and seafloor spreading are caused by plate tectonics. So that's kind of the overview thought. But convection currents in the mantle are what drag the plates across the surface. So these convection currents that we saw yesterday are what are dragging these plates apart in this case. So if these plates are moving apart, if this African plate is moving this way, and this South American plate is moving this way, and they have matching fossils on each coastline, then it sure seems like at one point they were together. And that's the next page in the notes. This is called Pangea. And if you take all the evidence and you take all the shapes of all the continents and kind of fit them together, and then add in all the fossil evidence of what matches what where, this is what we think Pangea looked like. So we've got the United States and Mexico, but then you've got South America kind of shoved up in the Gulf of Mexico there. Africa, which is gigantic, by the way, is beside all of them, with Europe pressed right on top, and then Russia and China and all those Asian countries are way up here. The only thing that doesn't really make sense where it is India is right here next to Antarctica. What we're going to see is that India is just cruising up into the Chinese plate because for some reason this one's moving really fast. Now, Pangea, the most recent supercontinent, from about 200 million years ago when all the land masses were connected. So this is what we call Pangea. So here we have Pangea, and over time, these are millions of years are cooking by, you can see that the different continents, the different plates start breaking apart. And all of a sudden, right here, if you watch right here, the Atlantic Ocean just starts opening up. Here goes India. India's just cruising, and eventually India crashes up into Asia, and you get the Himalayan mountains, which are still growing today. If we go on, okay, I said this one is important. We're using lots of paper up here, but if we want to look at the evidence of plate tectonics, we'll see that there are lots of different things. For example, the coasts of Africa and South America appear to match up with each other. That one's pretty easy. Matching coastlines. Okay. The next bit of evidence that we have has to do with the age, heat, and magnetic orientation of the seafloor. So if we look at the seafloor here really quickly, here's a picture. right here's the mid-Atlantic ridge. Right here is this. So right between these two plates that are breaking apart, we call that the mid-Atlantic ridge. Well, what we see there is that there's little plus signs and minus signs. That is that the rocks have recorded the magnetic orientation of the Earth. And we see that these two match each other, and they both point north. But if you get into slightly older rocks, here, the magnetic orientation is flipped, meaning that your compass would point towards the South Pole during this time period. And then it would be back to the North Pole, back to the South Pole. Okay? What's interesting is that these two bands, so this band and this band, match each other. So these are the same age, and they have the same magnetic orientation. These are the same age, and they have the same magnetic orientation, and outward. So as you move away from the ridge, as you move away from the brand new rock, the rocks get older, and you can see that the magnetic field has flipped. So in your notes, that's the bottom part of your notes here. The magnetic orientation of the rock switches as you move away from the ridge. Okay? So magnetic field switches as you move away from the ridge. Moving upward, we also have the rocks near the ridge are always the youngest, and they get older as you move away from the ridge. So these are the youngest rocks. These are always the oldest rocks out on the continents. That suggests that these two plates are pulling apart and new rock is forming in the middle. Last thing, rocks in the mid-ocean ridge have the highest heat flow because they recently cooled. And so basically the heat is concentrated in the middle because that's where all those hot rocks are cooling. So we're going to go on to the next page here. Now, so if this is the ocean floor, okay, and here's a compass. So right now, let's say the compass is pointing north, okay? Well, as these plates pull apart, there's going to be a gap here, and some new rock is going to form there. And what happens is inside of the rock, you can see which way the compass is pointing. You can test the rocks and say, hey, look, the atoms in here were pointing this way. Okay? But over time, what ends up happening is that the Earth's magnetic field switches, and our compasses would end up facing the other way. Now, this rock would stay pointing this way because it's solid rock, but as these plates pull apart further, what happens is the new rock records that new information. Maybe it's pointing that way for a long time. Okay, and then it switches again. New rock forms in the middle. Records this. And here we are today. The rocks that we see forming in the middle, like every other rock, is facing that way. Here's the youngest rock, and here's the second youngest rock, and way out here on the outside, this is the old rock. So we have the young rock forming in the middle here. It gets older as you step out, and we're seeing in the rocks that the magnetic field switches from time to time. So our compass pointing north isn't forever. Eventually, in the next few thousand years, it will switch and be back to that way. That's it. And so based on that, you should be able to say, okay, now I can see why the middle would have the highest heat flow, because yeah, that recently cooled. The rocks near the ridge, near the middle, are always the youngest, and they get older as you move away from the ridge. Okay, those outside ones are the oldest. And the magnetic orientation of the rock switches back and forth as you go along. Okay, so that's evidence number 2. Evidence number 3 has to do with what's called the ring of fire. Now, if the Atlantic Ocean's getting bigger, here's the Pacific. The Pacific must be getting smaller. And we're going to be talking about this more, but these are called subduction zones. Subduction zones in the Ring of Fire. 90% of all earthquakes and most volcanoes happen here, where the Pacific plate is getting pushed under into the earth, basically. The earth isn't getting bigger. If it's getting bigger in one place, it's got to be getting smaller in one place, in a different place. So this is the Pacific Ocean getting pushed down, and that's where we see almost all earthquakes and volcanoes, called the Ring of Fire. We're back to this picture of if you pull these different land masses together, if you pull South America up to Africa, and India down here, and Antarctica up along this way, with Australia off this side, you'll see that the fossils that we find end up matching up. And this is what an old ecosystem would look like. Okay? If these were put together 200 million years ago, this is like where the ecosystem is over this time. Fossils of the same land-based organisms have been found separated by vast oceans, because right now there are vast oceans between all of these land masses that we've pulled together. That's the four evidences we have for plate tectonics. It's a big idea, and it's a driving idea here for earth science. And basically everything else we learn about in this unit has to do with what we just learned about in this lesson.